been here about 5 years, and I think I finally learned how to eat hush puppy and grits and all of those good things that are good for you. At least everybody keeps telling me they're good for you. I asked Scott Crossfield if they were good for you, and he says, heavens yes, those things will do wonderful things for you. So I'm still waiting for what that's going to turn out to be. The National Aerospace Plane Program discussion this afternoon will include Scott Crossfield, Paul Siz, and Jeff Sponable. Dennis Moore was scheduled to be on the program, and I haven't caught up with Dennis yet. But we'll proceed, and if he shows up, we'll insert him in the program. I'm sure he's as flexible as the rest of us are. The National Aerospace Plane Program, from my perspective as chairman of this session and help to organize it, can develop the technologies and provide an aircraft that is capable of normal runway takeoff and landing, and that can undertake hypersonic single stage to orbit and or transatmospheric flight. As many of us that have been involved in the program for a number of years to help move it through the various congressional wickets and the wickets within DARPA and NASA and the Air Force, recognize that this has been a tremendous challenge. And I think that unto itself is a reason to have it included as part of the discussion relative to space as we know it and as we desire to see it continue to expand. Our first presenter, person that is going to discuss some of the historical significance of what he's done and give you his perception of the National Aerospace Plane, is Scott Crossfield. For those of you that don't recognize the name, and I seriously doubt that there's anyone out there that doesn't, it is a world-renowned pilot, having flown many research aircraft missions, starting with the X-plane, including the X-15, which he had a hands-on involvement in the design and the development of it, to the research airplane. And he actually flew it, and to that I'm very envious. I'm not sure I would have had the courage, having flown it at Mach 2, and I believe Mach 3, is that correct? And I kind of kidded him when he landed out at Huntsville Airport, having flown his Cessna down here from Virginia, how on earth a person could have the patience to fly at almost stall subsonic speeds when he spent a lifetime flying at high altitudes and high speeds. Scott has served as a technical consultant to the House Committee on Science and Technology on issues related to civil aviation and research and projects that are too numerous to mention. And it is truly my pleasure to introduce Scott Crossfield, and without an agenda, so just hang in there. I'm sure you'll appreciate what he has to say. Scott, welcome.
Thank you very much, Julian. My honor and pleasure to be here. Anytime I'm board-sided with one of these things, I lose my presence of mind, so I made a couple of notes about what I'd like to talk to you about today. And they're intended to provoke, so you don't have to throw anything. Plus the fact that I want to get across the idea that our problems with the NASA today are not technological, but programmatic and bureaucratic, political. I've been working with the concept of the research airplane that has become the NASP X-30 since the cancellation of the Aerospace Planes Jr. in 1963. In 1978, we presented a concept to the chairman of the Science and Technology Committee that was for 4 program stages to develop a hypersonic research airplane of unlimited speed, utilizing what would become known later as the two-point propulsion cycle. In the early and the middle 80s, we were working with the Aero Propulsion Lab. Copper Canyon was at work, and we held 2 very well-attended congressional breakfasts on what was to become the NASP X-30. The first of those was sponsored by our chairman here today, Julian Campbell, who was one of the program's staunchest advocates over most of its life. One of the X-30 technology arguments for critical civilian requirements was the SST replacement that was called Orient Express, so named by Dr. Gus Weiss of the National Security Council. Ralph Nader made it SST in the vicinity, so we let Ralph Nader design the Orient Express. Everything that he objected to was in the spec for both. While the Orient Express was to come out of NAF technology, it was a sophisticated design that was very feasible. And most of what I knew about its configuration and technology, I learned from Paul Sidds, who you'll hear from today, who had a very good handle on that technology. Well, the reason I dwell on this history is that more than 20 years, in countless meetings like this one, I thought if I could get this kind of engineering talent out of these towers of Babel and into the design room building an airplane, I could have flown to orbit and back in NAS derivatives myself as a passenger reading the Washington Post by now. The entire research airplane program would be a continuation of the NAS, from the X-1 to the X-24, up to 30 years. Its total cost is less than $500 million. To date, we've spent $3 billion on NASP, and we're still voting on its requirements. With Apollo, we proved that we can engineer anything we can write the requirements for. And the requirements for the X-30 compared to Apollo, originally funded by Congress, that X-30, are very objective and very simple. The X-30 is a research airplane, research meaning an experiment to learn, experience, and confirm the physics of the concept. It's an airplane that is designed to, please note the word designed to fly from a runway to orbit, return to the runway using air-breathing propulsion. That's its only purpose, to learn how to do that. Its payload was a necessary crew and its flight test instrumentation, and no more. The same academic community, and in fact some of the same people who had heaped scorn on the X-15, the Mercury, the Gemini, Apollo, and the Space Shuttle, and now the space station, have become the nemesis of the X-30. It's axiomatic that our successes are in indirect proportion to our ability to excuse or explain our failures or reasons for not doing things. We've developed an explanations of that nature to a fine art. I remember just in my lifetime the impossibility of cantilever wing structures, of passenger protection over 15,000 feet, of air-breathing engines over 20,000 feet, of penetration of the sonic barrier, of zero-G tolerance, of Brayton cycle productivity, of survival of secondary radiation at 70,000 feet, survival of meteorite showers at 120,000 feet, of the thermal thicket, of the electronic penetration of the Kenley heaviside layer, of psychological survival of detachment ad infinitum ad nauseam. All of those were impossible things to conceive of and do. Well, the energy equations will show that about a pound of hydrogen burning atmospheric oxygen will place about 7/10 of a pound in orbit, assuming reasonable estimates of performance characteristics of ground. All we need to do is engineer the aircraft. If we fall short, we will certainly learn why and know what to do about it. However, we know a great deal more about X-30 technology at this stage than we did about the X-15, Mercury, Apollo, and the shuttle at the same stage. What we don't know is where to get the leadership and the determination to just go do it. The demand for a detailed spec of the unknown as a prerequisite to do a research program has turned the NASP X-30 into a program NASP X-30 program into a funding money cow with very fuzzy objectives. Last fall, the House Committee on Science, Space, and Technology decided to hold a hearing on a proposed bill for NASP to get it back on track. The bill was to authorize the entire program requirement by schedule as a program, a cost, and a schedule to give Congress a grasp on what they were buying. This was to avoid the endless annual promises about how good it was going to be if Congress just gave the program a lot more money each year. The NASPEC 30 had grown an order of magnitude in size from its original proposal. Its cost was rising exponentially. Actually, it went through 3 times the original proposal. Its schedule was slipping more than a year for each year, and that didn't seem to be a very acceptable way to keep the program on track. Chairman Brown's proposed bill suggested a straw man, and please note that I said a straw man. We called it the 5-5-50 bill. 5 years, $5 billion and 50,000 pounds, take it or leave it. Pretty much like the original results of the Copper Canyon study that was sold to Congress in 1986. This program acknowledged risk with no padding whatsoever. Risk, though it seems to be, is a currently deletable expletive. There's a body of reputable opinion and engineering capability that is willing to build the X-30 to the 5-5-50 plan risk, but they themselves are a little more comfortable going 80,000 pounds to substantially reduce that risk. You think that's unreasonable? Rensselaer one time said that you could do the NASPEC 30 program for 29,000 pounds, take off to its weight. The nation sorely needs the X-30 technology. There are many proposals out there to do everything but the X-30 to avoid making a decision to go ahead and design and build. I submit that we'll be tinker-toying with this technology until a Franco-Russian ticket agency is opened on Pennsylvania Avenue with a foreign vehicle to go to orbit for his Mars. Thank you.
I dare ask if anyone might have a question. I dare ask Scott if he would be willing to take one, but are there anyone with a question that you might like to pose at this point? Sounds like you've made some converts.
What do you think about the chances of this thing being pulled off by us?
What do you think about the chances of this thing being pulled off by us?
The chances are very good. All we have to do is decide to do it and go do it. But apparently the atmosphere that we live in today, particularly with the new budget and administration situation, doesn't give you an awful lot of optimism that we're going to go do it. And it doesn't have to cost a lot of money. If we would recognize this is not a weapon system, this is no kind of a system, just a laboratory experiment. We could save a tremendous amount of money just by virtue of understanding that, where an experiment has in its answers negativism, failures, and successes. But I think it can be pulled off if we just decide to go do it. The original proposal for the airplane, and was very reasonable, price felt careful, was $4 billion. It's gone through $15 billion. The original first flight date, 1995. It's gone by 2003. The original weight of the airplane was estimated at 50,000 pounds. That went up to 1 million pounds. It's back down to 500,000. But you know the success that you people from Huntsville do, but the lack of success is in direct proportion to the number of work stands and engineers you can get around a vehicle prior to launch. If you can keep it small and simple, it's going to go a lot oftener, a lot more reliable. But it can be done.
We got one more question. Time for one more.
Yeah. What about other countries? How are they getting ready to build something?
What about other countries?
I don't know that other countries are designing and building a NAS per se. I do know that Shagi and Shan have the capability to do it just as well as we do. Wouldn't be surprised with their new arrangements they're making with the Russians, with the French brokering their technology capability, that they may move out and do it. They have gotten ahead of us in that they've done flight tests of an engine equivalent to the HRE that was once carried, to be carried on the X-15. I think, and some other people think, that they're advertising that as a red herring covering up a more sophisticated NASA-type vehicle that they're doing in the background. Don't ever believe that the countries Sikorsky and Seversky are technically illiterate. They have capabilities and wind tunnels that are way beyond what we have right now. They just maybe don't have much more smarts instruments. But it can be done by other countries just as easily as it could be done by us if they wrote the spec and determined it and went at it to do it.
Okay. Thank you, Scott. Do you want to sit down in the audience and so you can see his presentation and the others? I think it's pretty safe to say that we are on the threshold of a new generation of advanced technologies that can enable the high-speed commercial supersonic flight in single stage to orbit from a hypersonic flight standpoint. And this new adventure is in store for all of you and this nation if we have the resolve to pioneer the return to the research airplane program for atmospheric and space flight. That's just a little endorsement from JVC relative to what Mr. Crossfield had to say. The next speaker on the program happens to also be an acquaintance of mine. We have traveled worldwide in pursuit of technologies to England and other places, and Paul and I share a very mutual regard for this particular program and what it could mean to this country. Paul has moved on from his position as a senior fellow at McDonnell Douglas to president of Hypertech Corporation out of St. Louis, and he was one of the principal, I guess organizers is a good word, procrastinator, organizer, shaker and mover, certainly someone that brought to bear a lot of technological expertise and wisdom. Currently, in addition to being the president of Hypertech, he is professor at Parks College in St. Louis University, and I think some of his students are over here. Welcome to Huntsville. Paul, welcome. I'm glad you're here, and whatever you need. Would you like the mic down there?
Yeah, please.
Okay.
This is really about aerospace planes, although the title may not immediately look like it.
We're making progress at glacial speed, but we aren't redesigning the system, okay? I think that'll give you enough cord to get there.
Enough for to hang himself.
Right.
Okay, let me reinforce one thing about what Scotty said. If you believe for 1 second that other countries cannot build a hypersonic or a high-speed airplane in orbit, we need to send you back to grade school because they can't do it. And right now, 2 years ago when I was in Russia, there were places that I could go to and I saw some very interesting things, including the thing that Scotty alluded to is there are other engines over there that are not the engine that are being reported in Aviation Week, and they're quite sophisticated. Secondly, I'm going back in July. A lot of the areas I went over there in 91 are now closed to me. And they had a sign in French over the doorway which says, "No Americans welcome," or German or Korean. Because you can buy a Russian scientist for $25 a week. They have capabilities in research that make our stuff look like we're still playing child's games. They have very, very sophisticated research. You don't see it because it's in isolated silos. It was never intended to be publicized. It was never intended to have any impact on society or anything else, just the group that funded it. Don't ever kid yourself. Anybody who can beat an adult all over the United States playing chess at 6 years old is not dumb. Okay. Now, I think the age at which aerospace planes are going to be funded by a national organization and used exclusively by that nation for their own purposes are dead. Just as Boeing 747s or McDonnell Douglas DC MD-11s or Airbus 320s are not the sole use of the Air France. They're sold all over the world and everyone uses them for transport. And I think we have to understand that the future of space planes is going to be that kind of future if we're ever going to be successful. Now, if we're going to have a coalescence, in and I'm a believer of the convergence of history. There's a situation right now that's analogous to the Panama Canal, the third attempt to build it. The chief engineer came from building the railroads through the West. Excavating was a way of life. Tesla had just put in the power station at Niagara Falls with polyphase, lightweight motors and generators. By the way, the 1897 generators are still running up there. Walter Reed had found a way to lick yellow fever. They were making some progress on understanding where malaria came from. They drained the swamps. And a group of very innovative people created a mold with an attached cement plant that's literally slid down in a continuous casting process and cast all the canals. It was extremely ingenious. The doors on the canal are buoyant. They support their own weight. And a 40 horsepower Tesla polyphase motor opens and closes those doors to this day. The Tesla motor was made by Westinghouse, and that's why GE had to find Steinmetz, is to get polyphase experience. Now, we're at a point in history where the elements that we could coalesce exist all over the world. I'm not going to explain every one of these. I'll show you a couple of them. These capabilities are running in hardware, and I'll show you some of those. Now, let me explain a couple of things. A liquid air cycle engine is a hydrogen engine in which there's a problem. You can't burn hydrogen in an engine unless you vaporize it. So you have to find a source of heat to vaporize it. We have the atmosphere out there. When you use the atmosphere to vaporize the hydrogen, it does a funny thing, it liquefies. And so you create liquid air that you can now pressurize with a turbo pump and pump into a rocket chamber, and you have an air-breathing rocket. And I'll show you the impact that might have. The second thing on there is called a rocket-based combined cycle engine. Now, I was burning hydrogen at 7,000 feet per second when I was a young lieutenant. It's about 1961. And it's not a problem, it works, and I was always amazed that the rocket people always killed any attempt at air breathing because rockets run on test stands and they're simple, cheap, and everything else. And I'll show you what my opinion of that is. If I want to play the game, I'm going to build a rocket-based air breather. And what that simply means is that the inherent motive force that provides the impulse to the air to work at low speed is a rocket. It could be an air-breathing rocket, but it's still a rocket. If I wrap a duct around the rocket, I have an air-augmented rocket with some very good specific impulse, and we'll see what that looks like. So that's the two. Everything else is buried in the systems and the materials. Materials, I'll make one comment. When I was in Russia in 1989 and 1990, at that time I was the chief scientist for the National Aerospace Plan McDonald. The big project was the Materials Consortium to develop rapid solidification rate materials for application on mass. When I went into NPO Composite and NPO Energomash outside of Moscow, they're sitting in their display area and being manufactured in their shop areas were 11 different rapid solidification rate alloys that were already flying on the Energia rocket. So, you know, people can invent things. Now, there's the elements that I think can coalesce. We have a problem. The problem is that the vehicle that we're using to get to space is an expendable vehicle. And just like pioneers like expendable vehicles, the pioneers in space used expendable vehicles because they only wanted to go one way. There's not very many records in history where the Conestoga wagons came back from Sacramento or from Oregon to St. Joseph, Missouri with payloads. It wasn't worth the effort. Now, they were cheap. It didn't cost very much. You could get fuel on the way. And in fact, the byproducts actually helped fertilize the plains. But there was a problem of economics. You cannot build the future of the West if that was what you were relying on transportation systems. It was great for pioneers. So if you take these classes of vehicles and you put them in the context of the 1890s, 1880s, it was shipped, and the chart comes from Russell Hannigan over in England, who has written a lot on space transportation. Can you imagine if you were in the 1890s and you wanted to ship produce, or you wanted to ship commodities from New England to San Francisco via clipper ship, and that was the characteristics of the clipper ship. First thing is you'd have to pay for the entire ship, and it only got used once, so you would have to keep building ships. But can you imagine if you couldn't test the ship prior to sailing? Will it sink when it launched? Those things do happen. And the problem is that although we use expendable vehicles for pioneering, to set up a non-pioneering industrial transportation system, they don't have the right characteristics. So what I'd like to introduce you to is some potential of the elements that are out in the world today to be coalesced into several different kinds of systems that actually go both ways. Now remember, if you go back in Scientific America and you look at the 100-year and 75-year comments, you'll find that whether it's the transportation system, or whether it's Edison's electrical distribution system, or whether it's automobiles that will never go beyond the city limits, all of the scientific community and those who were, quote, were in the know, said it was impossible because the investment in the infrastructure, that is, creating the roadbeds, was so enormous it would never pay for itself. But we know that's not true. In fact, it was just the opposite. Without the infrastructure investment, there never would been an industrialization of the West. And once that was there, businesses, about 80% of the businesses that were derived from this activity were never envisioned by the people that were using Conestoga wagons. Rick Chappelle this morning talked about, as you explore, what you find out and what you do are things that you've never envisioned in the past. And that's really what we're talking about. So I can't tell you about what we're going to discover in the future. What I can talk about is what is the analog to this device that goes to and from space. Now this is not a new idea. I could not find this chart anywhere in the United States, so a friend of mine in Germany found it for me. And this is from one of Von Braun's charts from about 1950. And to quote, the technology is different, but we had the dream of flying back and forth of the train. Now, this is 1950s technology. This is red fuming nitric acid and aniline, and it's not the kind of things you would build today. The dream was there, but the tracks weren't laid. So what I want to talk about is how can we keep the dream alive? And I agree with Scotty. There's absolutely no reason we can't do this. The problem we have is it's very comfortable, again, as Dick Chappelle said, sitting on the fence watching the birds fly. It takes no effort. You don't have to do anything, and it's free. If you really want to do something, then you've got to go out and do it. And that takes two things. It takes the ability to make decisions and the ability to understand that as you learn to walk or fly, you're going to trip and fall flat on your face, and you pick yourself up and do it again. It's only through mistakes are we going to learn, and we've forgotten that. The people from this city who put Apollo on the moon did the impossible, and everyone knew it was risky, but they understood what they wanted to do in very clear-cut engineering terms and kept their focus on that, and they didn't focus on the fact that it's risky. By the way, if you read the latest National Geographics and what cowbirds are doing to the songbird nests in some areas where the southern warblers are and the Baltimore Orioles, they cease to exist. as the cowbirds throw out the songbird eggs, they raise the cowbirds as their own, and in 3 generations there's no more songbirds left. I sometimes feel like the Washington bureaucrats are doing that to us. Now, let's not be said that other nations can't think of things, even if they are not as wealthy as we are. This is from the Space Institute in Bangalore, India. This was based on work that John Ahern did in 1957 when he and Carl Builder went into Roy Marquardt and said, you know, the air through this engine can't be slowed down anymore if we want to fly any faster, because it's going to blow the engine apart. It has to go through the engine supersonically, and once we do that, we might as well use some of this hydrogen to liquefy some of the air, and those numbers are exactly correct. Now, they haven't built anything yet, but they have worked out the problem, and they've worked out the problem correctly. If these guys went to someone who could build this, it would work. Now let's go to somebody who can build one, in fact, who has. And that's a place called the Calcutta National Aerospace Laboratory Facility right outside of Sendai. In 1985, they built their first large lace heat exchanger, about 1 meter cubed. When we were over there in '89, we saw it run. A group at ISIS, which is the Institute for Space and Aeronautical Sciences, built a expander cycle engine that just fits lace very nicely, and that has 470 seconds of ISP. On the left is where you start. On the right is what you develop when you really want to get serious about this. Now, this system's being designed for a vertical takeoff vehicle called H2. If I take the solid strap-ons and throw them away and put on liquid strap-ons based on a lace rocket, it's an air-breathing rocket to about Mach 6, H2, which can now barely lift what Ariane 4 lifts, now becomes a reusable first stage and lifts about 15% more than what Ariane 5 lifts, and because it's an air-breathing first stage, it's recoverable. The costs go down considerably. In spite of the fact that everybody says liquid oxygen only costs 5 cents a pound or whatever it is, if you don't throw the vehicle away every time, you make some big progress. Now, why do you do that? Why you do that is because you make about 22 pounds of liquid air for every pound of hydrogen that flows to the engine. If I take out, just look at the oxygen portion of that, you see that instead of a 6-to-1 onboard ratio, which is what most hydrogen engines in the United States have, if I use the more advanced engine, which is the one here with the internal compressor in it, I'm only carrying about 1.5 pounds of oxygen for every pound of hydrogen. So there's 4.5 pounds of oxygen weighing 91 pounds a cubic foot that are not on board the vehicle. It becomes now an air breather at liftoff. And if, like Delta Clipper, I use it on a vertical landing, it becomes an air breather at landing. The specific impulse in this portion right here is 3,500 seconds, which is equivalent to a General Electric 404 jet engine at full military power. Specific fuel consumption of 1 pound of thrust per pound of fuel flow per hour. That means I can now hover without depending on a lot of oxygen. In fact, I can even run out of oxygen. I can have no oxygen at all and just dump the air into the rocket engine, and I can hover enough to recover the payload. So now, rather than having to lift off and go to orbit or fail, I can lift off, check everything out. If it doesn't work, I can set it right back down again. And the reason I can set it right back down again is the fact that it doesn't weigh as much. Now, this is some charts my students did. There were 3 of them that were involved out of my design class. That's one thing about having 40 students in a design class. I can get all kinds of things done that I never could get done in McDonnell Douglas because I couldn't afford it. Students cheap, they're free. Now, if you look at the left-hand side, it's something like Delta Clipper with a very advanced expander cycle engine. This isn't what they're flying with, but this is what they could be flying with. if I just go to Mach 3 on waste, it's really not worth it. If I go somewhere between 6 and 8, you see the empty weight and the hydrogen weight go down a little bit, but not that much. The real issue is the oxygen weight goes down. On the right-hand side, the left-hand side, what that is it's the empty weight of something like a DC-9 with a gross weight of something like a 747-400. That's awful tough to get a landing that done, especially since you can't control vertical speed that well. But if you go like Mach 6 to 7, it's like the empty weight of a DC-9 and about the gross weight of a 727-300 or a 757. That's possible to do. It's possible to build a light enough landing gear that you can lift off. If something's wrong, you can settle back down. So as long as you go less than Mach 6, the airplane can fly back and land again. When it does land, it isn't an oxidizer limited landing. It's an air-breathing landing in which you get 3,000 seconds out of your fuel instead of 400 seconds. So a lot longer time. The size doesn't go down so much. What goes down is the weight. And this is the result of their sizing. Now the only reason I show this is this really isn't an issue on vertical takeoff. It shows what happens when you introduce an air-breathing rocket. Not an air-breathing ramjet or scramjet, but just an air-breathing rocket to Mach 6. The gross weight goes down by 2/3, and the empty weight goes down by something like about 45%. That becomes a very affordable, easy vehicle. Those funny-looking things on the side are inlets that are used for the lace system. There's no rotating machinery involved. There's no air quality. There's no distribution quality within the engine. All the air has to do is get inside to the heat exchangers and it'll work. Now, that's a vertical takeoff. It's limited to 2 places in the United States, like Cape Canaveral and Vandenberg. Can you imagine how many people would be sitting in this audience if the only 2 airports available for takeoff in the United States were Vandenberg and Cape Canaveral? You'd have to take a train to get there, and then you could fly to Huntsville or something. You know, it doesn't work that way. If you're going to have commercialization, you've got to have sites to fly off of. So as Scotty says, the real goal is to fly off of runways. We know how to do that. It's not a technical issue. In fact, there are no, I'll be very positive, there are no technical issues that would prevent you from flying to space. There's only issues of people who want to sit on a fence and watch the birds fly, and that's a lot safer than trying to do it the right place. Now, are other people doing it? That is not the American flag on there. This is from a consortium of Japanese companies. This is a combined cycle rocket-based engine, and if you see there is the lace heat exchangers. This is the ramjet where the liquid oxygen air goes down into the run. It's a very nice, interesting airplane. Is it exactly what we would build? No. Is it feasible? Of course it's feasible. Are they building it? Not yet. What they're building is their vertical takeoff lace system so they can get some experience. Now, what kind of performance can we get out of that, and what can we do with it? And I want to point out one thing. There's a point on high-speed airplanes that's important. This whole part of the engine has to have hydrogen flowing through it in order to control, I don't like the word cooling, in order to manage the thermal environment so that things don't overheat. There's a speed with which you can fly, with which the compression side of this vehicle is underneath the radiation equilibrium temperatures, underneath the materials temperatures that's inside the engine. Where those 2 points meet is about 3.9 kilometers a second, or about Mach 14. If I fly faster than about Mach 14 and a half, then the rest of the underside of the vehicle has to be thermally managed. This hydrogen has to flow through it and cool it. Less than that, it only has to flow through the engine. And I'll show you why I talk about that. If you're going to do something like this, you have to fly fast enough, because if I carry too much propellant weight per empty weight, the landing gear and the wing size to get me off the runway is a problem. In order to get the wing size down, I need a propellant to empty weight or operational empty weight. That includes the empty weight plus the crew plus all of the residuals plus the payload. Needs to be about 4.5. HOTOL was 4.6, and it used a trolley because it couldn't get a wing big enough at a runway speed that you could, if you put a big enough wing on to get the runway speed down, you couldn't afford the payload weight. If I want to get off with the right takeoff gear and the right wing, I need propellant to operational weight, empty weights under 4. And that means I have to fly to at least Mach 10. And the other limit, not limit, but the other desirable place is right about in here. So this is the bracket point where you would like to have an airplane that flies. You have to fly at least 10, and if you don't want additional complications, you want to stay below about 15, light the rocket and go to orbit. Now my students, I say I got all kinds of students, been working on this. I'm working on this paper that'll be given at the International Aerospace Plans Conferences at Munich in December. And my students have gone in for the spatular wave riders. Now Scotty doesn't like spatula noses. They were invented in England, but they do reduce drag. This is the wave rider. It's designed for 7 metric tons of payload, about 15,000 plus pounds. The design point is Mach 10, at which it has a maximum thrust minus drag, that is maximum acceleration. The other thing about students is they can build wind tunnel models. There's a picture of a subsonic wind tunnel model before it was finished that went into the wind tunnel to look at some landing characteristics. It's essentially a captured shock vehicle. The conical shock is captured by that leading edge. There's the engine cowl right there, and the compression ramps are inside here. Now here's the kind of results we're getting for that with the 7 metric ton payload. It's not quite as optimistic, I shouldn't say optimistic, it's not quite the same thing that Scott talks about, but it's close. Zero is an all-rocket, high-pressure expander cycle engine. That is not an American engine. That's either a Japanese engine or a Russian engine. And that weighs nearly over a million pounds at liftoff. And it has about 17% of its empty weight, that is without payload, is payload capability. If we look at the point where we get this thermal balance, where we don't have to cool the rest of the airplane, then that's a Japanese rocket-based combined cycle engine. This is a Russian one. And Carl Builder, as I said, was one of the original groups that went into Roy Marquardt and said, I got a new idea, and that's based on his analysis. And as you can see, there's not much difference between them. About 35 metric tons with a 7-ton payload on board, and a gross liftoff weight of about 110 pounds. That's about 65 metric tons of fuel. That's a 7 metric ton payload, so it's about 9 pounds of hydrogen with some oxygen on board for the orbital mission, because remember, this has to maneuver in orbit for every pound of payload. Now, I want you to remember this one number here, which is for 7 metric tons for a vertical takeoff wave rider that looks like that. I need about 350 metric tons of liftoff weight. Now there's another way to get free of the launch point, and that's build a 2-stage orbit vehicle. If you lived in Europe, you wouldn't want a single-stage orbit vehicle because you're at 50 degrees north latitude, and geotransfer orbits 7 degrees, and Earth and space station orbits 28 degrees. So you have to burn an awful lot of fuel to get down to those low latitudes if you have a rocket. So you would like a first stage that would get down there reasonably quickly, and then you only have the fuel on board to get to orbit. So there's a number of people that have worked on, and this came from a paper that I did at Huntsville about 3 years ago on foreign space planes for the NAA meeting that was down here. That's why it still has McDonnell Douglas Corporation on it. And everyone has their ideas. What's surprising is they're not all that different. The argument, by the way, is if you see the two below, the France and the USSR, you see that they have a glider with an expendable second tank. The Japan and Germany have a glider that has a tank included in that. And the argument is, should I pay for a tank that I send to orbit and have to thermally protect to bring back down? It's cheaper to use the expendable tank if you can get away with it. Now, these are all sort of unusual gliders, at least to me. What we're going to talk about is a two-stage orbit system that is based on the X-24C flight dynamic FDL7 type of stuff. This is Wright Field many years ago. Al Draper, Dick Newman, Val Dowling, and a number of people like that that I can no longer remember. This has a lift-to-drag ratio at Mach 25 of 2.7. If this were attached to space, by the way, the original space recovery vehicle that I worked on in 1964 at McDonald was based on this configuration. With a lift-to-drag ratio of 2.7, it could break off of any space station in any arbitrary orbit in any position and land in the continental United States from the orbit that it was in. You never had to wait. And I think that is absolutely crucial. As Lisinski says in Russia, the only place you're ever going to have a firing orbit is where there's people breathing oxygen. And so if you can't get them out of there to depressurize the station, you're going to be in deep trouble. And I think you need, that held 13 people. And and there was a rule that we had when we worked on that, is you couldn't have any more people on board than what you could get into that. Now here's the engine that I would recommend for that. This is the RD-0120. I took this picture at Baikonur at the Energy Assembly Complex building 2 years ago. This engine has some interesting characteristics. It's made by, Kimi Abel Kamanaki, which is Automatic Chemical Machinery Company. It has the test site they have in their major facility has 44 test stands, and this engine has been tested in a series of cycles. One engine has been inspected after every firing for a complete launch. If there's nothing wrong with it visually on the outside or with some simple checks, it's put back on the test stand. And if there is something that needs to be refurbished, it's then refurbished. A single engine has now gone through 64 firing cycles without failure, with refurbishment when they need it. The second engine, this engine is certified by the Russians for 3 launches without refurbishment. You can tell what they were working on. They have taken this one engine and they've gone through 34 3-launch cycles where they inspect and repair after each third flight and put it back on the test stand. So one of these engines has been through 34 3-launch cycles with only refurbishment between those 3 launch cycles. It's a very reliable engine. 250 atmosphere stagnation pressure. It has 7 methods of cooling inside the engine, 2 of which have never been seen before in the West. It uses all welded construction, uses ceramic coatings almost everywhere, and is an extremely interesting engine. As the Germans did on the V2, the Russians start all of their engines on tank pressure, 2.5 to 3 seconds on tank pressure. If the engine doesn't light and function, they just scrub the launch. If it does function correctly in the first 2.5 seconds, only then do they light the turbo pumps. This is a full expander cycle engine, uses hot hydrogen, uses no combustion products to drive the turbines. About 471 seconds vacuum ISP. It's a very interesting engine. The red one you see in the background is an R&D engine, and it's hooked up a little differently. The white nozzle ones are their production engines. Now what we did with that is we took that and put it into a into this vehicle here, and we used the wave rider as a first stage. As we sized it, both of these weigh just a little over 100 metric tons, and this is the correlation that came out of that with respect to staging speed. And you see there's the Zanger point at 366 metric tons. Now, you would think we would get a number similar to the single-staged orbit. The SSTO was about 110 tons. The engine stopped at 14 and a half. The rocket was then lit and went on a rocket trajectory to orbit. As you see here, the best speed is about between 12 and 14, and the weight is about the same. It's about 120, 140 metric tons at 12, and about 103 at 14. Is it possible to do this? Yes, it's possible. All of these things I've talked to up to this date require a leap of faith with respect to either the first stage or the single stage orbit or the wave rider, or a leap of faith with respect to the engine. And so we're not prepared some of these days to make leaps of faith. So I want to show you one that doesn't require a leap of faith. And this is what I'm going to end the presentation on. The names you see at the bottom are some more student names. I've never had so much fun in my life. I can get things done I never wanted done. I never could get done before. This is a group of 3 people that took a wave rider based on some Air Force work and put it on top of the EN-225. The EN-225 will take 250 metric tons off the support points. The Russian work that was done in loading this indicates at 275 metric tons, the doors will no longer open. The major cargo door at the back and some of the doors up in front. So that's the limit that you're going to get on that airplane. You can get 250 metric tons if they take out the system that is used to move cargo inside the military version that weighs about 20 metric tons. And so with that out, you can put 250 metric tons up there. You see, that's really not a very big vehicle. That's about the same size as the one I talked about. That was SSTO. In fact, the next team decided to take the SSTO Verge that they did the wind tunnel testing on, and indeed put it on top of the EN-225. That's 110 feet long, and it weighs about 105 metric tons, about half the weight of what the Antonov can lift. And again, having some students around, they wanted to build wind tunnel models. We did some subsonic wind tunnel separation tests on that. They built the best equivalent we could get of the 225, and you see how nicely that sits on top of it. Again, because it's an air-augmented rocket liftoff, an air-breathing rocket, start the air breathers up before you separate at low power. You can pull the Antonov up into a steep climb just before it reaches thrust minus drag equals 0. And as it does that, it'll fall away, and you light the air breather off to full power on the wave rider. They simply pull right apart in a couple of seconds. The thrust-to-weight ratio at liftoff of the air breather is about 3 to 1, so it climbs like a scalded rabbit. Now, the important thing about that is that it is relatively insensitive to what you assume the thrust-to-weight ratio of the air-breathing propulsion system is. We actually use 20. Whether you use 35 or 30, or even go pessimistic and go 15, it really doesn't make any difference. The Antonov can carry it easily. Now, a good non-gimbaling high-pressure rocket engine is about 90 to 1. A gimbaling engine is about 69 to 1 thrust-to-weight ratio. So to think that you can get a non-gimbaling 90 to 1 thrust-to-weight ratio engine inside a box for an air-augmented rocket, and it weighs about 1/4 or 1/5 of what the rocket weighs, should be reasonable guess. Now that still requires a little leap of faith because of the air breather. Let's go one more step. Let's take a tried and true glider. This is Lizino Lazinski's. He has flown 34 of these at near orbital speeds, about 24,000 feet per second, glided them over Russia and recovered them. You've seen 1 or 2 that have landed in the Indian Ocean, but most of these were recovered internally to Russia. He uses scrapped boosters for this that came out of the ballistic missile program in the former Soviet Union. This is a unique bird. It has a one-piece silicon carbide graphed carbon nose. Total thickness of that between webs is about 3/16 of an inch. All internally braced and supported made in one piece. Very interesting. Very lightweight tile. This fin is a very interesting fin, and it's unique to the former Soviet Union. It's really unique to Sagi and Koalescing. As you remember, M2F2 and HL-19 all rolled very badly when they landed. For M2F2, it actually rolled down the runway. Koalescing experienced that in about 1952. And so what he did is build an airplane that flew with a jet engine that proved that if you built a variable dihedral horizontal vertical tail, that supersonic speeds and hypersonic speeds, it was up here to stay out of the streamline flow so it didn't burn up. And as you got lower and lower speeds around Mach 2, it started to come down. And when you landed actually with 5 degrees negative dihedral, it lands with no pitch and roll problem whatsoever. That is unique to the Soviet Union. I wish we would adopt that. There's more flight test data on that vehicle than any other vehicle I know in the United States or anyplace else. That was designed, by the way, for coincidence, to get 13 people out of Mir 2. No matter, it seems we get the same numbers. Now here's his approach. That's the AM225 again, with a tank that's based on the front end of the Energia tank. That tank is physically made and sitting in Ukraine right now. And if you could settle the disputes between the Ukraine and the former Russian and the Russian Republic, you might get your hands on it. The glider does not exist. The glider is larger than the little research gliders that I showed you. The problem with it is that you carry 6 pounds of oxygen in that tank for every pound of hydrogen. So the gross weight of that, if that would be the wave rider, is 354 metric tons. If I take the wave rider tank out, so that I have that disposable tank that drops to about 300 metric tons, that's still more with a 7 metric ton payload than the AM225 can lift. But let's take that Japanese invention called LACE and let's do this. Let's take these 6 engines you see here and power them on hydrogen. First thing that happens is the thrust goes up 15% and the specific fuel consumption drops significantly. The entire center of that airplane is empty. The total launch crew for that vehicle is 6. And if you think that's not correct, I can show you some tapes from Baikonur in which for the standard Soyuz launch, whether either Progress capsule or the manned Soyuz capsule, it takes 6 people to launch their flight, and the rocket and payload are put on the stand 8 hours before they come off and launch. It's a neural net computer system controls the whole launch process. From 12 noon on, when they begin fueling, there is no human being anywhere on the launch site. It's all done robotically. Now anyway, let's put the hydrogen engines on that thing, and let's put the LACE system not inside the glider, but inside the antimatter. We now can make about 100 tons of liquid oxygen. We separate out the nitrogen. Here we can do easier. And we can store that inside that tank. So now our vehicle that you see weighs, the wave rider that weighed 356 metric tons. If we take the oxygen off, it only weighs about 210. It can lift that. As the hydrogen fuel comes off and burns, the oxygen goes on board the tank. The airplane can physically fly with the 400-ton metric payload up there. The reason it can't fly with it is because it can't get off the ground with it. So what we do is we load the airplane up as it flies out to the launch site. The launch site's not over land. It doesn't influence anyone. And more importantly, if you have a rescue mission for space station, and you have to worry about phasing and worry about orbital inclination, you simply fly to the node, launch this, and you can rendezvous with the station on the first orbit. That means that you can, from the Koalescing's design is, from the time you get a warning that you've got a problem on station to the time that this vehicle rendezvous with it is 7 hours. And that starts making some interesting sense. It's a very versatile system. If you were the Prime Minister of Indonesia and you wanted to show the Indonesians that your new Indonesian communication satellite, which supplies all of your school children with their high technology learning, no longer has to be shipped to either the United States or to Peru to be launched by foreigners. You fly this airplane into Jakarta, you do whatever ceremonies that the local government thinks necessary, you put the satellite on board and you fly out of Jakarta and launch it. You now bring the services to wherever they are. This is exactly what FedEx does. And I think if you're going to get commercial, that's what you're going to have. Now I'm going to end with this because this, I think, is the counter chart to where I started. If you had this class of vehicle with lace in the fuselage hydrogen fuel, it would be reusable. You could test it prior to launch. You know the airplane is useful, it flies all over. You can safely abort. If the rockets don't light with tank pressure, you can just come back and do it the next day, not 45 days later. You can save the cargo. You can demonstrate your reliability. It does go in both directions. More importantly, if you're on hold, the cargo doesn't stay in the payload bay for 4 to 6 weeks waiting for the launcher to be fixed. If there's something wrong with that launcher, you simply take it out of the payload bay and put it in another launcher and launch it. And I think you might have something that's interesting. Now, is it possible to do this? This is a chart that came from TRW when Golden was the head of it. Okay? If we're going to do this, we have to keep the light bulb from turning out. And if you notice, it starts with, I have an idea. And you notice all the naysayers, a word of caution, a little too radical. We tried something like that once. Let me play the devil's advocate. As the guy says at the end, well, it was just an idea. There are 100 people out there turning off lights to one person that can keep the light lit. When I started out in the business, my bosses always kept my light lit because they said, I don't want to know the reasons it won't work. I want to know the reasons why we can make it work. Today, all I hear is, yeah, I know you think there's 1 or 2 reasons it can work. Here's a whole list of things why it won't work. I guarantee you, I cannot find any set of circumstances where I can guarantee myself that I can cross the street out in front of the Hilton Hotel and not get hit by a car, unless I block the traffic and do all these illogical things that would make me not want to live a very useful life. Now, if we're not careful, if we keep shutting the lights off in the United States, then one of these days, and I have Lake sitting right here in the audience, one of these days we're going to see that fly to orbit, and that's a microwave-powered spacecraft based on plasma propulsion. And one of those right now is flying in the former Soviet Union. I don't know if I can go over and touch it, but I've seen the video of it. And it won't be too long if we don't enter the 21st century in the United States with that railway train to space, so people can look up and say, this is what we've accomplished, this is what we can do, we've made a tremendous economic breakthrough that's providing us with a lifestyle and an economic base that we've never envisioned before. If we can't do that, then someone else is going to do it. Thank you very much.
Well, do we have any questions? We maybe have time for one, possibly two, and if we've got a gentleman over here that's got to go catch an airplane after he makes his presentation. Yes, sir.
No, that would have been the next hour. An air-augmented rocket. Okay, let me go through and just give you a couple numbers. A rocket, since all the propellant goes through the engine, has a specific thrust, that is thrust per pound of airflow of about 450 in vacuum conditions. That's the same as the fuel flow because all the propellant goes through the engines. If I build an air-breathing rocket, that is, I build a LACE engine, the specific thrust stays about the same. It stays about 400 pounds of thrust per pound of volume of mass flow through the engine. But now the fuel flow is less, and the specific impulse thrust per pound of fuel flow is now like about 3,000 seconds. So I get 3,000 pounds of thrust for every pound of fuel.
That's the LACE.
That's the LACE rocket. Now, if I stick that LACE rocket inside a box and induce air through it at low speed, I go up to about 4,500 seconds, and the thrust falls down to about 360 pounds of thrust per pound of airflow. So I essentially can create an engine that has the thrust of a rocket per pound of airflow at the specific fuel consumption of an unaugmented full-power turbojet. Now, if you think that's impossible, if you go to Laurel, Maryland, and you go see Fred Billick at Johns Hopkins University, he can show you some test data that was done in about 1955, 56. Because I was working at McDonnell Douglas then in working on Talos ramjet missiles, and Typhon, which followed that, we flew 13 missiles between around 56 at Mach 4.5 to 5. Our program was canceled because it was so successful it outflew the radar, but anyway.
Thank you, Paul. You have a question, one more question, and no answer.
Why did they cancel that successful program?
I don't think either Scott or I have the time to go into that. I don't know why they do that. Do you know why they do that? Why do they cancel successful programs?
Threaten someone's vested interest.
We have two gentlemen up here who refuse to answer that question on grounds that it probably would incriminate them. Well, I think from the two previous presenters, you see that the challenge is that kind of challenge that has always stimulated American response to these kind of initiatives, and the successful response to this challenge certainly, I believe, from what I hear, will help us assure America's continued leadership in aerospace, in the flight technologies, in the trade, and in economic competition in the world. And even though we're here in Huntsville, Alabama, we see international competition emerging and growing stronger and carving out market share from our industries here. So kind of keep that in mind as you listen to some of these presenters. The next presenter that will close out the session, and he truly will close it out because as soon as he finishes, he's going to be out of here in a heartbeat to go catch a plane, is Major Jess Sponable. And I apologize for not having a complete bio on him. All I can tell you is he's certainly a very well recognized member of the Delta Clipper program and has been instrumental in numerous technologies, some of which he has moved here to the Marshall Center, and I'll let him explain that to you. So please welcome Major Sponable, and I hope you can finish up and get out of town on time.
I got 20 minutes.
Okay. Slide across here.
Turn the lights on.
I wanted to come down here for several reasons. By way of introduction, I started out my career out of Annenberg way back when, and spent time launching atlases and went down to Space Division and worked on shuttle and numerous other systems. Ended up in the NASA program in 1986 and spent 3-4 years there. And then I moved and came up to this program I'm working right now, Single Stage Rocket Technology, out of the Ballistic Missile Defense Organization. I have seen, well, let me put it this way, I know where all the skeletons are buried. And there's a lot of concepts for how you can get to space. The question I would ask you to ask yourselves is two questions. One is, can I do it reliably? And two, can I get the recurring operating cost as low as possible? And don't settle for a 10% improvement or a 20% improvement. Drive for order of magnitude reductions. Those are the two fundamental issues that face any new space launch system. Everything else is peripheral to it. I'm going to be a little controversial here, sir. I don't totally agree with all the perspectives that have been made, but I certainly reminded me of a whole lot of things over the past 8 years, going through the NAS program and seeing all this happen, and seeing the frustration that exists about what happened in that program. There are technical issues that make some concepts easier to do and cheaper to do than others. And what I'm going to do is talk about my perspective, which starting through and going through all of that, I was pretty much impartial going in. I gyrated is the best words towards what I think is one of the right answers for a next generation space lift capability. And that is the program we're running out of the NVO right now called Single Stage Rocket Technology. It's not a big program, and I'm going to tell you a little bit about it. The basic idea here is that aerospace planes do not necessarily have to breathe air. They just have to fly in the aerospace environment. This is a concept for a vehicle that can take off and go to either suborbital or orbital altitudes, come back and land using rockets. This particular concept is McDonnell Douglas's Dalton Clipper concept called DCY. It takes off, flies into orbit, comes back into the atmosphere. It's not a rocket, it's now an airplane. It's coming back in. It has a cross range, the latest variant of that vehicle, of 2,000 nautical miles on reentry. That is a huge cross range, even for an air-breathing vehicle. It comes down at about, and this is only one way you might do this maneuver, but at about 10,000 feet, it turns on its 8 rockets on the back end, throttles them up to about 10 or 20% thrust, goes through a rotation maneuver, and then falls under controlled power to a landing at the landing pad, a vertical landing. That's not the only concept. There's other concepts as well that I'll talk about a little bit later. Well, we in the Ballistic Missile Defense Organization, I shouldn't say this, I'll get in trouble, but we call it BIMVille affectionately up at SDIO. It used to be called SDIO, and we went through a name change just a few weeks ago. What we did was back in about 1990, we started a program and brought 4 major contractors on board. General Dynamics, Boeing, Rockwell International, and McDonnell Douglas. We had them look at a variety of different single-stage to orbit, all rocket-powered concepts. And what we ended up with after a year, we down-selected to a McDonnell configuration, which is the configuration you see, and we asked them to go build a vehicle called the DCX. The DCX vehicle is shown in the middle there. It's reusable, locks hydrogen, uses 4 RL-10A5 modified rocket engines. It's got a very heavy structure made out of heavyweight aluminum. It's got an ideal delta V, for those of you who like those kinds of numbers, of about 8,000 feet per second, but it only flies in the subsonic flight environment. We're going to take it off out of White Sands this summer, and we're going to fly it through a variety of aerodynamic flight profiles. One of the key issues on a vehicle that has to come into the atmosphere nose first is how do you handle the aerodynamics of taking a barn door and rotating it through a 180-degree angle of attack and then landing. A very, very tough aerodynamic problem. Beyond that, when you really look at space and what we do in space and how I used to operate the Atlas systems out of Vandenberg, the shuttle down at KSC, we don't operate them the way we do aircraft. We have standing armies of people that stand around and nurse them. What we wanted to demonstrate with this vehicle was that there's nothing intrinsic to the technology of rockets or these kinds of vehicles that would keep you from operating them like an aircraft. And there isn't, and we're showing that. In fact, by way of an example, we have this vehicle right now out of White Sands Test Facility going through static testing. We went through 2 engine tests, all 4 engines operating at the same time in one day. An 8-hour turnaround time. Now that's an amazing thing. We're not just turning around the engines. We're having to deservice the vehicle, re-access the vehicle, go through the checklist, power up, bring the vehicle back up, put hydrogen blocks back in it, and fire it again. And we did that in an 8-hour time period. It's been a very fast track program. We spent roughly $15 million in phase 1, and the contract for phase 2 was a $60 million contract. Very small amount of money, very, very fast track. The corollary to that is we're not proving everything associated with single-stage orbit rockets. We're focusing on key issues that we think are important, that need to be demonstrated before you can take the next step. The key issues that this vehicle is really focusing on is the aerodynamics, some of the software, flight control laws associated with this kind of flight vehicle, and more than anything else, the operations and support associated with operating a vehicle like an aircraft. Now, this isn't a view graph, this is hardware. That's the vehicle being rolled out. We've got a couple of congressmen, in fact the man on the left of that is Congressman Brown, watching us roll the DCX out in Huntington Beach just a couple months ago. We've also flown it already in a sense. Just like in an aircraft program, before you ever took the aircraft out, you would hang it and you would rotate it, spin it, and twirl it, move it in a hangar environment off of a crane in every direction you can, just to make sure you've got all of the gyro packages and the inertial nav systems hooked up properly. Sure enough, we went through these tests and we found out that we had all of our software constants reversed. That's not the way you want to fly. We wouldn't have headed for China and we wouldn't have got very far. Well, we fixed them and went on with the testing. That's why you do that kind of testing. This is a picture of the DCX as well, sitting out in the open. I don't know who the person posing for the picture is. This is what we're really trying to do with this vehicle. We're trying to let me reverse the order of this. Show you one other thing first. We have more than just a vehicle. We have a vehicle, I want to call it a launch pad, but it's not really a launch pad. It's some people call it a launch simplex, a simple flight facility that we can operate out of. And we have a flight operations control center. The guy in the front of that picture, that guy is like a pig in heaven. His name is Pete Conrad. He's the third man to walk on the surface of the moon. And he's our flight manager on this vehicle. He just absolutely loves this program. And fortunately, I don't have to pay his salary out of our program costs. It comes out of the McDonnell overhead. But he's been a big supporter and a big fan of what we're doing. What I want to point out there on the Flight Operations Control Center is there's 3 people controlling this vehicle. From the time we put all the valves in the automated positions, to the time we start servicing propellants, we load the vehicle, we go through the pre-flight checks, the health checks, we fly the vehicle, we land the vehicle, we service the vehicle, and then we re-access the vehicle. Throughout that entire sequence of events, there's only 3 people, 2 of which you can see there, that are controlling the automated sequence of operations that are occurring. The third guy, and as usual, it's the guy that does the logistics, the ground support systems, is sitting in the background. This is all a mouse-driven, Windows-type environment. It calls up the screens. You see the valve colors change as it cycles through and does one thing after another, so you know the exact status of the vehicle as you step through it. But the guy in the back is the guy that's really operating a lot of the equipment, the facilities part that keeps the thing, makes it so operable, supportable, and rapid turnaround. So what we focus this program on is a series of demonstrations that address common needs. And whether you're talking about a scramjet-based vehicle, a lace-based vehicle, a rocket SSTO, or a turbojet vehicle, these issues are going to be common. One is keeping the infrastructure and facilities investment to a minimum. We spent, our goal was less than $5 million, we spent $600,000 total facilities investment as we report to Congress, and we report the right numbers. Be careful how I say that. Down to White Sands Army's missile range. Now there's another $6 million of mobile transportable equipment that's not classified as facilities that we use to support that vehicle down there. For example, our Flight Operations Control Center, some of our launch pad paraphernalia, which is not actually part of the facility, but it's things we haul down there. Responsive flight. We're going to as a goal, try and turn this vehicle around in 3 days. Now, I already told you that on the test stand at least, we succeeded in getting 2 firings off in 1 day, and that is really an amazing accomplishment. Fast call up. We want to be able to fly this thing routine, like you would an aircraft. The corollary to that is that because we're using a lot of older technologies, we built this thing quickly with not a lot of money, we've taken some risks. We have single string avionics, for example, on the vehicle because we don't think we'll need it. Because we won't fly this test vehicle forever. We'll fly it this summer and this fall, and that's it. The ground crew beyond the 3-person launch team numbers 25 to 35 people total. We don't have a standing army standing around servicing this vehicle. And reliability, we've tried to keep the vehicle as reliable as possible, but of course we do have constraints on it, and that we just have limits. We, for example, up until last week, didn't have an engine out capability on this vehicle, and the software engineers who were working on it have now figured out how to install an engine out capability. So at least while we're landing, if we lose an engine, we'll just shut it down, and we'll land on 3 engines. What we've done in SDIO is a series of stepping stones, if you will. We've taken the first step, and that's building and flying the DCX. And we've taken some risks. The way we're pursuing the program, very much, a lot of risk in things that we're doing. And we could lose this vehicle. We don't think we're going to. We think we've got a 90% plus chance of pulling off a very successful flight test program. But anytime you fly hardware, you run the risk of losing it. What we see as a next step, and it is not currently funded in the federal budget, is a vehicle that's just a bit bigger. It's still suborbital. It'll get up to the Mach 5 to Mach 10 hypersonic range. It'll have an ideal delta V of between probably 15 and 20,000 feet per second. And for those of you who keep tabs, 30,000 feet per second for a rocket-based vehicle is what it takes to get to orbit. For an air breather, it's about 45 to 50,000 feet per second, depending on what kind of an air breathing cycle you use. I think your LACE cycle would be substantially less than that. Right?
A lot more ISP.
A lot more ISP too, yeah. Beyond the SX2, what we would propose with this SX2 is we'll take 8 of these RL-10A5 engines that we're flying on the DCX, and we'll build an airframe just like what you need for a single-stage orbit rocket rocket. Same composite structure, same materials, same unit weights, and we'll fly that again and again. So we'll have a graphite epoxy tank, for example, for the hydrogen, and an aluminum lithium tank for the LOX. It will let us demonstrate in this small vehicle, which can be flown within 3 years at a cost of somewhere between $300 and $450 million. It would allow us to prove that you can scale that technology up to full-scale SSTO as the next step. It'll demonstrate aircraft-like recurring flight costs, $1 million a flight, or thereabouts, or $2 million a flight. It'll demonstrate high reliability. We're going to design it for high reliability, and it'll demonstrate the mass fraction issues associated with scaling up structures to single-stage orbit class vehicles. But even beyond that, another stepping stone is a full-scale, what we call a DCY, or government vernacular would be a YS3, to go out and full scale and prove that you can do that. I would point out that the McDonnell DC series of vehicles are certainly not the only way that you can do a single-stage orbit vehicle. In fact, the concept up on the right there is a Lockheed concept. It's been pushed by the Lockheed Skunk Works out in Burbank. It's a vertical takeoff, horizontal landing, all rocket-powered vehicle. It's an eye-watering concept, a very neat way to go do this. The temperatures, because of the way it's constructed, are re-entry are in the low 2,000 degrees. So you need no carbon-carbon, no carbon sick on that vehicle to re-enter the atmosphere. It's all alloys, and that's a neat concept. Rockwell also has a concept that takes off vertically and lands horizontally based on their shuttle experience and whatnot. But it is an all single-stage vehicle. The configuration you see there has an Aerospace engine on the back end. Well, let me just say, what makes let me step through that a little bit, and I'm going to jump to the end. What is SSTO and what's it good for? And then I'm going to back up and talk a little bit about the SX2 and how we would propose to get there as a next step. What makes single-stage orbit feasible today? Several things. Aircraft, reliability, maintainability, operability, supportability. This country has literally put billions of dollars into those kinds of advances in Air Force programs like RN-2000, paid soars. A lot of money has gone into aviation technologies. That's why we can fly across the country or even across the oceans for very, very small amounts of money today. And a lot of that money has been placed and used in the past 20 years. Those technologies don't care if you have a scramjet, they don't care if you have a rocket or a turbojet. It doesn't matter. It's just operability, supportability. Technology advances. Aircraft programs, V-2, ATF, Starship, Beechcraft is an all-composite airplane flying today in the commercial sector. We would propose that those kind of composite technologies need to be applied to space vehicles. And that certainly is what McDonnell has done with their DCY concept. The NAS program had a tremendous number of technologies that were brought online that directly support SSTO rockets. One perfect example is we're using a graphite epoxy hydrogen tank, which the NAS program actually built and tested with hydrogen in it a few years back. HAB Region is a little-known program that people should know more about. I'm going to tell you a little bit about what that was in a minute. It was a program run out of the NAS program. At the time it was classified. It's since been completely declassified. But it was a concept to build a single-stage to orbit all-rocket vehicle out of superalloys and titanium, not composites. The National Launch System, and of course, Ballistic Missile Defense Organization. And finally, when VMDO took this over, they took it over with no preconceived notions on what the answer ought to be. It's amazing how many studies we do in the aerospace industry where we come in and verify what we believe starting out. We looked at both vertical launch and horizontal launch systems. There was a real bias within the Air Force for a horizontal launch system. And obviously, we like airplanes. That's what we do for a living in the past. So we kind of leveled that playing field. We considered both winged and ballistic configurations, and we didn't restrict the engines to either the scramjet or the space shuttle main engines, as some of those earlier programs had. Well, here's some of the technologies that NASA has done. I already mentioned the graphite epoxy structure. Aluminum lithium comes out of the NLS program. Design codes, trajectory optimization codes. A lot of that technology is directly transferable to any future single-stage orbit system. This is the program I mentioned, the HAB region. There were 3 structures actually built. One was one in the lower right corner was a full-scale single-stage orbit structure made out of titaniums and superalloys. The two in the 2 adjacent corners, here and here, Boeing and Lockheed respectively, were 40% scale SSTO structures, again made out of superalloys and titaniums. All of these structures were brought in within 3% of their SSTO design weights. The loads were validated by finite element models. All of the articles were tested to destruction. What that means is we didn't have a 100% successful program. However, given that only $10 million was given to each of these contractors, and all of the contractors knew what the problem was, and all of them knew how to fix it, and all they needed was more money, it was a pretty successful program. And just the fact that they brought them in and waiting, and they were so close to making it work is amazing. But by the time we finished this program in about 1989, we were pretty well convinced that graphite epoxy and titanium aluminide and some of these other advances made by NLS and the NAS program would bring about fundamentally new kinds of vehicles. And that's about the time that we down in the NAS program heard that SDIO wanted to go look at some of these concepts, and we went up and started talking to them and showing them what had been done in the past. And they were surprised. This is a little more detail of, as far as where we're at today in this McDonnell Douglas design. The DCY here is about 132 feet high. It's got a aluminum lithium LOX tank, a graphite epoxy hydrogen tank, a payload bay 15 feet by 15 feet square by 30 foot deep in the middle of the vehicle. That helps the center of gravity issues and concerns. It uses a truss structure made out of graphite epoxy for your primary structure holding all the loads on the vehicle. That really helps get the weights down to that type of structure. And it is what we call a cold structure. It's got graphite epoxy face plates over it, and graphite epoxy is only good to 200 or 300 degrees. You've got to put hot panels over the top of that. We're not using any tiles like Shoto uses. We're using multi-wall metallics, honeycomb aluminum, and in the very hot spots, carbon silicon carbide. In fact, I think the Russians went on their space plane to fight. The engines are 8 identical booster engines. It's a concept. This is a simple expander cycle engine. It's burning only going on in one place in the combustion chamber itself, nowhere else in that engine. All 8 booster engines are the same, but on 4 of those engines, you have an extendable nozzle that comes down. That lets you take this simple expander cycle, which is a vastly simpler engine cycle than what you would see on the Space Shuttle main engine, and it lets you get better ISPs, better efficiencies out of that engine's trajectory average to orbit. The payload capability of that vehicle is roughly 20,000 pounds. There's another 10 to 15,000 pounds of weight margin in the design. And then if all you do is take the vehicle off once, fly it around the Earth once and land, another 10 or 15,000 pounds beyond that. So overall, you've got over 40,000 pounds of lift margin to MECO. You get a little more also by flying out of White Sands, which is at 4,000 feet of altitude. Unlike turbojets, rockets like to take off at altitude. You actually get about 500 to 1,000 pounds more payload for every 1,000 feet of altitude. What could I use that vehicle for? I want to state right now that, or what I could use that margin for, that payload margin. When I add all that up, I got 40,000 pounds of lift margin. I do not believe that we are ready today to go build a single-stage orbit operational system. Big difference between an operational system and a technology demonstrator or a research vehicle. We don't know how to operate a LOX hydrogen vehicle. We're learning something with the DCX, and it's valuable, but we need to learn it with the same materials, structures, technologies that are associated with a full-scale SSTO. That would be the next step. But if you were to go build that vehicle, and you were not to call, and you did not call it an operational system, called it an advanced technology demonstrator or an experimental vehicle, I would have 40,000 pounds of lift margin that I could take, and I could go back and I could retrofit parts of that vehicle with very near-term technologies. I would not need to necessarily use graphite and lithium for tanks. I'm not saying you shouldn't do that. I'm just saying I can mitigate risk and lower cost by going back and using conventional aluminum. On the engines, I can use heavier engines initially. On the TPS, I can use shuttle class TPS if I had to. I don't think it's a smart thing. Primary structure, I could go to a heavier weight graphite epoxy. There's a whole bunch of things I can do to lower the risk by using that weight margin prudently up front, and at the same time allowing pre-planned product improvements, things that I know I can change and fix and improve downstream. Another way I can use that margin is I can look at alternative engines. The RL200 is the simple expander cycle that we use as the baseline engine for this vehicle. The J2S is an engine that was built, there were 6 of them built. It's a variant of the J2 that was used on the Saturn moon rocket, second stage of that rocket. The J2S, 6 of them were built and tested on the ground, a little bit better performance characteristics. I still get a 21,000 pound payload lift margin with that J2S, 8 of those installed on this vehicle. If I go to the Japanese LE7 or the French Vulcain, I have throttling concerns, but they will work as well. SSME, you just can't throttle it enough for a vertical landing system. You can use it very nicely on a vertical takeoff, horizontal landing single-stage orbit vehicle. There's other concepts for advanced engines out there within the United States, and over in Russia there's an engine called the RD701, which is a tri-propellant engine. It uses kerosene, liquid oxygen, and hydrogen. It burns kerosene at sea level because kerosene is much more dense than hydrogen, and that shrinks the structural size of the vehicle. I can triple my payload with that kind of an engine on this kind of a vehicle. I'm going to go a little technical here, I'm sorry. You get these physicists, and I say that with disgust because I am one. who will take the rocket equation, which is the left-hand equation up there on the upper part of that view graph, and they take it and they solve it for structural mass fraction on one side of the equation. They set that equal to a constant, and then they scale gross weight against ISP. And they get this curve that goes off scale. That's not the curve you're looking at. This is the correct curve, the way it's supposed to work. What they don't understand is that what sizes these vehicles, any kind of vehicle, whether you're talking about an air breather, a rocket, or anything else, are flying propellant tanks. Nothing more than that. What sizes these vehicles is the amount of propellant you have in them. The other major issue is that you want to look at gross weight or dry weight. Dry weight is what drives your development cost, your production cost, and most of your operating cost on any aerospace system. So what I did is rescale this thing just a little bit. I put dry weight over on the left axis and went up and we modified and solved for propellant mass fraction, the amount of propellant in the vehicle, which is a function of delta V and ISP. And then you take the dry weight of the vehicle, which is a function of that amount of propellant that the dry weight of the structure has to enclose. It's a function of thrust to weight of the engine. Thrust to weight of a rocket engine at anywhere from 70 to 100 to 1, depending on the cycle, is a very important parameter. And propellant bulk density, that means the average density. The more dense you can make the propellant, the smaller the amount of structure that has to support it. And when you take all those things in and do the calculations, the physics will tell you that we are not on a very steep scaling curve with single-stage to-orbit vehicles. And that's the light blue down there at the bottom. If you're 20% heavier in structure, you come up to this red line. If you're 40% heavier structural weight, you go up to the blue line. The brown area is kind of where we were in the 1960s. If we had not built the shuttle, we'd gone out and built a single-stage orbit vehicle using J2 rocket engines. It would have been a 500,000 pound, 5 million pound below SSTO vehicle. And there were concepts proposed during the shuttle concept exploration studies to do just that. The yellow area is kind of where we were with that program called HAVE, where we're talking about titaniums and superalloys. You're down here in a pretty reasonable range. The blue area is where you are with these new composite structures, materials, some of the technologies that the NASA program has come up with. You can see that the ISP of the rocket we're using, because it's a simple expander, is actually 17 seconds less than what the Space Shuttle main engine ISP is. A lot of potential for improvement there in the future. Okay, so why do it? The NASA program, in my opinion, is a great example of a program that ought to be done for experiment and research and to learn how to do things. We don't know and won't know until after you fly such a vehicle just how good it's going to be in answering those two fundamental questions I asked earlier. Is what is the operating cost going to be and what is the reliability going to be? Those are fundamental unknowns that you really need to go build a vehicle and find out. The advantage of single-stage rockets is the technologies are much nearer term. There's very few unknowns in the technical area. The one unknown that we need to sort out is this mass fraction question. Can I really bring these vehicles in at the weights the contractors all claim that you can? There's fundamental differences of opinion between the aerospace contractors in this country and between some of our government scientists. And that's something that needs to be sorted out. The mission model that we currently fly today is less than 1 million pounds total to low Earth orbit. I'm going to talk now a little bit about the applications. Why would I build this kind of a vehicle? A vehicle with a 20,000 pound class payload captures 60 to 80% of the total payloads that we fly in this country to orbit every year. You can use it for a bunch of things, from base launch to looking at things, to other military missions, to private sector growth, to shuttle augmentation, even shuttle follow-on someday. 20,000 pounds captures every commercial payload that's out there today. And we've lost most of the commercial launch market today. If you look at the total infrastructure cost of what we fly to space today every year, it costs us as a nation a little over $10 billion a year, including Shuttle, Titan, all of our medium lift vehicles, all the small vehicles, Titan 4. If you take a single stage orbit rocket, and if you can operate it at two numbers, $10 million a flight, 0.996 reliability, not 5.9 like an airplane, not 0.96 like an expendable launch vehicle today, but just somewhere in between, 0.996. And just replace the medium lift vehicles, Delta, Atlas, the small Titans, you save a little over $2 billion a year. If you take it and you replace the medium lift vehicles and the shuttle infrastructure at some point in the next century, and I would not propose to ever even think about doing this until after you've got 100 or 200 flights under your belt, you really know what the cost and reliability is, you save a little over $6 billion a year. And if you don't believe the recurring flight cost of $10 million a flight, then bump it up to 20 or 30. You still save a lot of money, many, many tens of billions of dollars over a life cycle of 15 years. And if you don't believe the reliability of 0.996, move it parametrically down to 0.99, whatever you want. The point is that until you fly flight hardware, you won't know where to put those two peg points. And if you jump into an operational system too early, you're very likely to peg those numbers too high. You're going to come in and you're going to design a system that's extra safe, it has to work, and therefore you're not going to know how far down you can push the recurring flight cost, and you're not going to know how high you can push the reliability. So in my view, the right answer is to go build some technology demonstrators and see how far we can push. If you do that, take the next step with an advanced technology demonstrator. The analogy, and this is a chart pretty much out of the old NASA program, is like the old jets in the 1950s. As we introduced them, we introduced a host of dual-use military and commercial applications, from military Century Series aircraft to commercial operational jets, like the Boeing 707, the first commercial jet. Similarly, this ATD vehicle could support some suborbital tests, and perhaps even make some money in suborbital flights in certain sectors, university research. Certainly, BMDO has an awful lot of requirements for suborbital ballistic defense experiments that we could fly in such a vehicle. A military aerospace vehicle or and a commercial launch variant, something with about 20,000 pound of payload. There's numerous military statements of need out there for such vehicles in that class. And someday downstream a heavy lift vehicle. The other one there that's I'm going to go through, I'm not going to advocate this, but I just want to make sure you understand the technology. There's two things on here, one the heavy lift and a commercial suborbital freight vehicle. What the concept of a commercial suborbital freight vehicle is still very nebulous, still very unsure. But take something off out of Central Conus or anywhere in Conus, fly to the Pacific Rim, land in just a 30, 45 minutes later. And haul high-value cargo back and forth. You're certainly not going to haul very many people, though at least some would be interested in doing that. Why do I think that vehicle might make sense? Well, here's a chart that shows cargo over empty weight. And empty weight, again, is what drives your development, your production, and most of your operating costs. Cargo you want to be as high as possible. So in the commercial airplane world, a unit of productivity, measured productivity, is the cargo over empty weight of these vehicles. When you look at the McDonnell Douglas DCY using its gold weights, which are there on the chart, a little over 100,000 pound dry weight. You can see the red line extrapolating up. That's how the DCY scales up to larger cargo vehicles and how the empty weight changes as it goes. The DCY right now, compared to a 747 is shown in the enclosed box, it's a much smaller vehicle in terms of physical size than the 747. There's a lot of growth room here. Also, with the DCY, you're not taking off horizontally, so you don't have the fundamental limits placed on you of wing loading. airplanes, it's just tough to get them much bigger than 1 million pounds. The AN-225 that the Russians built, I think, is at about 1.3, but it's one big airplane and it's not cheap to operate. Rockets have much, much larger thrust per unit weight of the engines, so they have a lot of thrust and they can take off vertically very easily. The point of this is if you assume that the technology, the operations mature, the cost of hydrogen eventually comes down just a little bit. LOX is a non-factor of 5 cents a pound, cheaper than JP fuel is today. If you look to the future and envision these kinds of vehicles and assume that those technology and operations mature, then my own view is that someday these kinds of missions, both heavy lift to orbit and suborbital freight type missions, may someday come about. I certainly would not advocate that you try and jump. We kind of did that with shuttle. We jumped into a 65,000 pound payload vehicle right off the bat. We may have had a very different vehicle flying today if we stuck with a little 20,000 pound vehicle, which certainly was bigger than any satellite, almost every satellite we were flying back in the 60s when we started that program.
That chart back up and show us where shuttle fits on there in comparison.
Well, the shuttle is about a 600,000 pound empty weight vehicle. That includes the total stack, not just the orbiter itself. It's about 180,000 pounds on the orbiter. So the shuttle, I guess, would be off to the right side of that chart. Is that fair? That's not totally fair in that some parts of the shuttle, like the solid, you have different cost factors applied to them. So it's not in terms of cost, it's not a linear relationship. The other interesting thing about Washington these days is everybody's talking about what they call dual-use technology, defense conversion. They're looking for places to put people like me to work other than on the solid gold. And here you've got a program that can do a couple things, possibly. It'll develop a whole lot of technologies which will have a variety of applications in the near term. At the same time, when you do scale it up to SSTO, hopefully by about the year 2000 or a little thereafter, it allows you to leapfrog the foreign competition. Not even the Chinese Long March or the shuttle or the Russian Proton can beat your costs when you're talking $10 million, $5 million a flight. They can't, even with subsidized prices, beat that kind of cost. At the same time, you've got a vehicle that can take off out of Central Conus and be anywhere in the world in 40 minutes. That opens up a lot of opportunities for how you go out and do things, look at things, and do space transportation as well. So what we propose, though, is not to jump to a single-stage orbit system. We think that would be a mistake. You don't want to go to an operational system right now, nor do you want to do a pure research program. What this could be is an experimental prototype, flight vehicle, or an advanced technology demonstrator, is the current really popular phrase up in Washington, within the Department of Defense. It's also an operations laboratory for learning how to operate a reusable launch vehicle. I can't tell you how many things we've learned from taking a piece of hardware out in the desert and start firing off the motors down to White Sands. We've just learned invaluable things. When we started off, we thought we'd have to have a big water deluge system, an entire concrete pad. What we ended up with was a flat pad with a launch mount with a, $3,000 metal mount that we tied down. We have just a couple of iron steel plates that we use to deflect the thrust. We have no water deluge system whatsoever. It is a very, very Spartan facility. When you go out there and look at where we're operating out of, you actually get frightened, at least I do. And finally, it's if you keep this vehicle small enough, keep the cost down enough, because that small size, dry weight drives a lot of the cost, to potentially fuel a fly-off alternative concepts. Again, this is that vehicle. And I think I've already pretty well talked to it. If you build it, you do it right, it'll allow you to demonstrate the material structures, units, weights that can be scaled directly to a single-stage orbit. It'll allow you to show the integrated kind of performance features that you want. The RL10A5 is also a simple expander cycle LOX hydrogen engine, which is exactly the kind of engine at 10 to 15 times the thrust level that we want for these bigger vehicles. And of course, and most important, it'll demonstrate this aircraft-like ground and flight operations. Whether we end up going with a single-stage orbit or a two-stage orbit or any other kind of vehicle, if you can't get the recurring flight costs down and the reliabilities up, you're not going to have routine access to space. You and I aren't going to go anytime soon. The other advantage of this SX2 as a next step is it does use the existing RL10A5 engine we're using on the DCX, and therefore we can fly that vehicle in 33 months if the money's made available. And we're working hard to try and convince folks that sure makes a lot of sense. It would certainly be a competition. It wouldn't be just McDonnell Douglas. What that vehicle does for you, it enables follow-on operational vehicles, suborbital and orbital. It positions the U.S. aerospace industry to take advantage of that effort in a competitive international environment. It spins off a lot of dual-use technologies. Hydrogen is going to be, whether we like it or not, it's my view at least, the basis of a hydrogen economy in the next century, because we're not going to continue using fossil fuels forever for environmental reasons. It bolsters a sagging aerospace industrial base. A lot of the contracted work is in California, which is having real problems right now. So a lot of political reasons as well for pursuing something like this. And finally, we're talking with the Russians about some very interesting Russian technologies. They've got an engine called a D-57 built by Lyoka, which is essentially a single-stage orbit class engine, LOX hydrogen. A little smaller thrust than what we'd like. It's only got 88,000 pounds of vacuum thrust. It's throttleable from 40% on, operates at sea level, 77,000 pounds of thrust. It's for a small demonstrator V engine. It's a wonderful engine. They've got built over 100 of them, and they've got at least 6 of them sitting in a warehouse. So we've got someone over there talking to them right now about the possibility of selling 4 of them to us and cooperate. It would certainly be, in my view, a neat triumph for the United States and our former arch enemy, the Russians, to come together and build something that just stomps the heck out of the Japanese and the Europeans. And I hope if there's any Europeans in the audience that you'll do the same, back us. So we need the competition. At this point, I'm going to go into a little bit of controversial area, and this is just my view. I see an emerging hypersonic roadmap, and that is there's certainly a lot of technologies in the NASA program that have enabled us to do what we're doing in this program. Will enable the next step to single-stage orbit rockets. If you build a single-stage orbit rocket, especially a configuration like the McDonnell Douglas DCY, which is a conical configuration, which airframers, aerospace vehicles in the past have historically often tended to have that type of an airframe. If it's successful, well, for one, you jump to an SSTO system, and that SSTO system is going to save umpteen $billion per year off of our current operating costs, and it's going to hopefully open new markets. At the same time, you can take that basic DCY airframe, because the fundamental issue facing the NASA program today is how do they get, it's almost the same as the issue of getting into space. How do you get recurring test time at hypersonic velocities? It's tough to do. The only way to get there now is with expendable vehicles, whether they be suborbital sounding rockets or IRBMs or ICBMs. If you have this kind of a vehicle, DCY, with a 20,000 pound payload, and I say, okay, I'm just going to fly it to Mach 20, I probably have 100,000 pounds of lift margin in that vehicle, and I don't know how many tens of thousands of cubic feet that I can take, and I can modify that aeroshell, and I can put ram inlets and scram inlets, anything else, and I can have a flying test bed that will let me do just about any kind of hypersonic research I can on the air-breathing side, including the low-speed side. Lots of volume in these vehicles, and lots of lift margin if all you want to do is get to Mach 20. That would allow you to get the kind of technology base that you want to go as far as the next step for the next third. So once you get done with your DCY, my point is it may not be wasted. You may take it and use it to continue to explore air-breathing technologies. My own view is that single-stage orbits have their own niche. We've always talked about something with 20,000 pounds. You probably don't want to go much heavier than that for first-generation application. That complements Type 4, or if a space lift or heavy lift type system comes along downstream, it will complement that. At the same time, the NASA program needs to get through the X-30 research program and eventually build some Y vehicles of some type. And even by their own program estimates, probably aren't going to have any kind of an operational system before 2015 or so. I had a chart on comparing everybody to the rockets, but I thought I would skip that. RLVs, what I call RLVs, reusable launch vehicles, offer many potential benefits over today's ELVs. Higher reliability, lower operating costs. They support synergistic military and commercial needs. They're environmentally friendly. The only thing I got coming out of the back end of that vehicle is water. Yeah, you get some nitric oxide, but very, very minor traces. The uncertainties in design, I don't mean to trivialize this issue, there are technology issues here. But the uncertainties really center around the structure of component weights, the durability, reliability, cost, operating cost of this vehicle. The technologies are in hand to go address those issues and take that next step. The ops cost must be proven. We really get the reliabilities and the operating costs down. And that's what we're trying to do with the DCX, and we're trying to turn that vehicle in 3 days out in the desert. Pete Conrad at least thinks he can beat that goal, and I'm not asking him to yet. We think that the next logical step for spaceflight is a 3-year program to go build an SX-2 demonstrator. And we've been talking with a lot of folks, ARPA, the Air Force, Department of Energy, Sandia, and Los Alamos Labs, who are looking for new markets and things to do, and even the National Aeronautics and Space Administration, some of the folks right here at Marshall Space Flight Center. So, and there's a lot of smart people out there that can make this happen. We just kind of need to pull them all together and push. And that's what we're trying to do with this program. Thank you very much.
Great. Now, I know you must have a question. Good heavens, we did have one right at the beginning. Yes.
The SX-2 prototype. Yes, sir. Is there any thought been given to mating it with a 747 carrier or a Russian carrier for high altitude takeoff? And speaking.
No. One of the problems you get into is there's a million configurations you can start talking about, and they're really irrelevant. The issue is, can I operate this thing reliably and cost efficiently? I can always put a booster of some type on it downstream if I can't make the mass traction for SSCO. The problem with mating things is when you mate things with manned aircraft, you start getting into major issues with flight safety and integration issues. And we did this whole DCX program for a little over $60 million. And if we'd have tried to fly it off of the 747, it would have been $60 million integrating it with the 747. It's a whole lot easier to, and then the other thing you need to understand about staging is staging provides you a performance advantage, no question. In fact, I can take that DCY and I can fly it on a suborbital trajectory to Mach 20,000 feet per second. And then I can pop out an upper stage with a payload on top of it. And by doing that kind of a staging maneuver, if you will, I can get a 40, 60,000 pound payload in low Earth orbit from the DCY. So you get a performance advantage from staging. But if you look at the dry weight of a two-stage vehicle versus the dry weight of a single-stage vehicle with roughly the same payload, roughly the same technologies, same requirements, you're going to see a very small difference. Gross weight on a two-stage vehicle comes down, but all that is pound. It doesn't matter. So in my view, at least, we need to answer the fundamental question first, which is reliable, low-cost access. Then and only then would you go to a two-stage vehicle, and only if you absolutely have to. My own opinion is, you saw those scaling rates, that if we build this SX-2, that will peg very, very closely what the weights are going to come in at, and then you can sit down and figure out whether or not you want to go to a two-stage or a one-stage vehicle.
How many times did you go to fly DCS?
We have plans to fly it through the summer and on into the fall. We've got $500 next year to continue the flight test program. My guess is we'll either run out of money or weather first. I'm not sure which down there. We will, as a goal, I've told the contractor we'd like to fly 15 times. I think realistically, we'll probably in that length of time. And this is very typical of X-aircraft. They start off with very, very low flight rates, and then they start going exponential downstream. And we're flying something that's even more experimental than an X-aircraft. I'll be happy if we get 4 or 5, personally. Because we can still demonstrate the turnaround. And at this point in time, without even flying, when we finish our testing at White Sands Test Facility, the static testing, we will have accomplished over half of the total objectives we set out to accomplish, including demonstrations of some of the operability and turnaround issues associated with this vehicle. There is a parachute on this vehicle, not on the bigger vehicles, because it just gets too big real fast. This is a 20,000-pound lightweight vehicle. We use it only in that rotation. Well, we can use it any time, but we do not want to use it. It is a contingency situation only. There's unknowns. It may come down and it may break if we use that chute. I give us, this is just my assessment, 50-50 chance of keeping the vehicle alive with the chute. Nonetheless, because of going through that rotation maneuver and just the fundamental unknowns associated with the aerodynamics, we wanted to have the ability to recover the vehicle going through that rotation maneuver. So that's what we do. Chute's only good above about 7,000 feet. And the first several flights, we will not go over hundreds or 1,000 feet.
One more question.
How many times would you fly it if you had more money? I mean, if you could fly it as many times as you wanted for tasks, what's a reasonable number before you start getting the mission?
Well, did you you heard what I said, that we have single string avionics on this vehicle?
Yes.
I don't know. I mean, what I need to do is what we need to do. Because there's a super team out there flying this thing. And I'm not anywhere near as smart as some of those guys are. What we need to do is go out and fly it a few times and take a look at it and see how it's wearing and what the characteristics are, see whether or not we can keep flying it. There's some folks here at Marshall who have talked about possibly picking it up and just keeping on flying it next year. I'm open to that, but I worry about trying to fly something that wasn't designed to fly forever too long. That's why you do that SX2 step. That's why you go to fully redundant avionics, things like that. Full engine out capability. We have a partial engine out capability. You need to design a system to last for a long period of time. And we did our best on the DCX, but we had limitations, money limitations, no other limitations, money limitations in terms of doing it.
Thank you very much.